so I'll be doing a quick review. Okay, so I'll be doing a quick review of what we studied in the last lecture. We studied the basic idea of molecular orbital theory and how the framework works for basic homonuclear diatomic molecules. We talked about basic molecular orbital diagrams of H2, and we talked about why He2 doesn't exist. We talked about all after this, and we talked about boron, diboron, dicarbon, and dinitrogen. We talked about the curious case of sp mixing. I'll review sp mixing for a while. sp mixing is actually the interaction between the 2p and the 2s atomic orbitals in individual atoms, which essentially causes the reversal of energy order as we talk of. I just illustrate it for a while because we are short on time today. I will try to cover as much things as I can. Say I illustrated from the example of V2. I draw it out like this. I won't draw 1s because it's 4. I draw 2s here. I draw 2p here. 2px, 2py, 2pz. Now, when I think of these orbitals, as we talked about overlapping extent, we think of the 2pz when it combines with the 2pz of the other boron atom. We think of it forming basically a stronger bond when we compare it to the pi set because of the overlapping extent as we talked about. These overlap for only this region, but this overlaps head on and overlaps completely for this complete region. As we talked of in the valence bond theory idea, we have directly borrowed it from there because it works. As we thought of it, we would have expected the sigma 2pz, similar idea, similar orbitals are here as well. I'm not drawing them for being quick. The pi set, and this is the sigma bonding molecular orbital. We expect it to be lower than the pi set, but actually, what happens in the case of boron, carbon, and nitrogen, this thing goes above. Now, why does this go above? Because when you see, although this doesn't really contribute to the bond order, but this orbital is still here. The anti-bonding sigma star because of this 2s, this is still here. And when I fill electrons, this sigma and this sigma star being closer to each other in terms of energy also gives us the implication that these are closer in terms of say distances as well. This gives us the implication that these orbitals are going to repel. These are going to repel, yes, but to top that, this 2pz and this 2s, these are very close in terms of their energy, so they can interact with each other as well in something called a second order orbital interaction. These orbitals being close to each other, the wave functions of these orbitals can also interact with each other, and this thing can come a bit lower, this thing can go a bit higher, and this penalty is paid after the molecule is formed. This leads to these orbitals being much closer than they would have been initially when we were talking about the picture without the sp mixing phenomena that we are thinking of. These become even closer, and this repulsion actually pushes this sigma above the pi set. This is where you see the order reversal that we talk of in the case of sp mixing.
Yeah.
That is
2p sigma and 2p pi.
yeah.
Will switch exchange the place of the energy levels. Right? So it will be exact same, or like there will be some deviations.
No, exact same नहीं है. I'm just saying that this sigma star, because it repels this. because it repels this sigma these sigma orbitals. These would try to go far away. Sigma star orbitals and these sigma electrons and these sigma star electrons, these are going to repel because of their proximity. And when things repel, as you know, energy increases, and as energy increases, both of these would be pushed far enough in terms of their energy so that their repulsion is minimized. This thing would go above enough, which is after it has crossed the pi set, it can now rest in peace. Which is why this sigma, when it goes above, it feels relaxed. That is when we see the order reversal. Now, as a consequence of this, we see this order reversal when we are talking about V2, C2, and N2. Now, why just these elements? Why not oxygen? Why not fluorine? Just because of the fact that the inner orbitals, the 2s orbitals, and the 2p orbitals that we are talking about, this gap, it increases as you increase the atomic number, because these 2s, as we talked of in the first lecture, these 2s electrons are going to be much more penetrated as the atomic number increases, as protons are going to pull them even more, as these are going to shield the further electrons. This thing is going to get more and more penetrated, which is also the cause of things getting more and more electronegative as C increases. Also, something to expand on, I didn't talk about the molecular orbital diagram of O2 in the last class. This has some intricacy that actually this shows a property of oxygen that doesn't agree when we talk of both valence bond theory and molecular orbital theory. When we were talking about the valence bond theory picture, if you draw oxygen, you will see a sigma bond, you will see a pi bond, and here is an oxygen. When you try to fill in electrons, as you know the electronic configuration of oxygen, you will see two lone pairs on each of these oxygens. Now, by seeing this picture, you would expect oxygen to be, when we talked of the magnetic nature of molecules or atoms or whatever you want to call them, we talked of unpaired electrons, the spins when they don't cancel, we talked of it. And these lone pairs, as you see, none of these seem to be unpaired per se. They are in a multiple of 2, which is why you would expect this thing to be diamagnetic. That is, it doesn't interact much with the external magnetic field as we apply it. But when you see liquid oxygen in practice, it actually goes away with those north and south poles when you put it in between them. Now, when you think of molecular orbital theory, it solves this problem. Now we'll see how. Now you guys are going to help me here. When you think of this 2s, you think of this, then we talk of this pi, Now, as there is no sp mixing kind of phenomena in the case of oxygen, as we discussed earlier, the Pz is going to be as low from the pi set as we expect it to be initially. Now when we start filling in electrons, we have 2p4, I suppose. Yeah. So when we start filling in electrons, we have filled, I suppose, 4 electrons here, and I start filling in. These are, say, you have to fill How many electrons do we have to fill? Let's start filling in. Second, let's see. Yeah, we are done. So yeah, as we see in the highest set of orbitals, we see two electrons being unpaired. Both of these electrons are unpaired, their spins are not cancelled. And this is what causes the paramagnetic behavior of oxygen as we know it. Now, this is where valence bond theory and molecular orbital theory don't agree. As we were, very much appreciating the valence bond theory in the last lecture, this is where they disagree. Now, also a notion that I maybe skipped, which is not very necessary to be honest. This is something that you will require in organic chemistry per se. But for now, I'll just say these terminologies. This means highest occupied molecular this means when you start filling in electrons in the configuration of orbitals that you formed just right now for oxygen, when you do it for anything, any molecule, then the highest orbital that you are going to fill, the highest energy orbital occupied, is going to be called the highest occupied molecular orbital. Similarly, the orbital just after that, the energy state just after that, is going to be called the lowest unoccupied molecular orbital. Now, why this should be important to you? Why does this concern you? Now, when you think of reactions, when you think of say any sorts of reaction throughout chemistry, what is it essentially? It is the transfer of electrons, and transfer of electrons from one molecule to another. Now, there is going to be something that has the electrons to transfer. There is something that is going to have enough empty orbitals to accept those electrons. Now, how do you assess if a reaction happens or it doesn't? Now, when you think of it, the entity that is going to donate electrons, that is going to be the starting point of the reaction, should have say the HOMO of that molecule is relevant to us because that has the electrons that are going to be transferred. Now, the thing that is going to accept electrons, the LUMO of that thing is relevant to us. If this gap, the energy gap between the HOMO and the LUMO is too much, then the electron transfer becomes very unfavorable for us. Because as you know, when two orbitals, when essentially the transfer of electrons is happening, what is happening is these two orbitals are essentially combining in some sense. Now, when two orbitals are going to combine, as we discussed in the last lecture, they got to have some sort of energy match, along with a symmetry match. They got to have some sort of an energy match. Now, if they want to, if I think of this as the HOMO, if I think of this as the HOMO, if I think of this as the LUMO, if this gap that we are talking of, if this is too much, then these, if this gap is too much, then these cannot combine to give orbitals of such sort in the new molecule. Then we talk of the feasibility of a reaction. As we talked in the first lecture, we talk of the spontaneity of a reaction. This won't be relevant, much relevant to you when you study inorganic chemistry, but you'll thank me when you start studying organic chemistry the next semester, because this feeling is what drives the flow of organic chemistry essentially. Also, if I was to talk about this thing as well, I would also like to mention one thing that is something very niche, but I think I should mention it. When you add electrons to a molecular orbital, its energy is generally going to increase. Now why is that? The energy is going to increase because the electrons that you're going to add would be much outside, much farther from the nucleus, and there are inner electrons, and the effective shielding, the effective nuclear charge on those electrons that you're going to add is going to be lesser than it was for the outermost electrons initially. That is why when you add electron density, to a molecular orbital, I'd rather say MO, you add it to the MO, what this essentially does is it increases energy of that orbital. Now this might not be always true, but we are not talking of intricacies here. This is the general principle that follows from our intuition and is also seen a lot. Now the real deal. We talked of one of the heteroatomic molecules, we talked of HF. Now we'll be talking about the mysterious guy, CO, carbon monoxide. Now, as you know, as we have built our intuition from the past, that the more electronegative an element is, or as the Z increases, the inner orbitals are going to be much lower in energy when compared to others. Now, also one thing to be noted down here is that carbon, in the case of carbon, 2s and 2p are close enough to be mixed, but in the case of oxygen, that is not the case. So now we need to be careful about it when we draw the molecular orbital diagram of carbon monoxide. First, we'll build it from the scratch. We'll write the valence bond configuration of both these elements. We'll write 2s2, 2p2, we'll write 2s2, 2p4. Right. Now, let's start from here. We see carbon, we see oxygen. But I think of it, I think of very careful while using the board, because this thing gets cluttered very quickly. But when I think of it, I'll see, because now why am I drawing these between them? These are somewhat results of computational observations as well. That because carbon and oxygen are not that far away in the periodic table. That is why the difference of energy is not that much as we saw in the case of hydrogen and fluorine. Fluorine was much lower than hydrogen, but oxygen won't be as low as that. This is something we see from computational observations as well. Yeah. So here we have the set. Now as this is going to be much lower, so I'll draw it here. Yeah. So now, what is the most intuitive thing you should do? Now, one thing that I have not represented very well here, these 2s orbitals, these are not very close by, as close as you see them. This must literally go down the board. This is much lower when we compare it to the 2s of this, say, carbon. So it cannot bond with it. Now, what is going to happen is, we see the phenomena of sp mixing. First, as we are considering the atoms, we'll see the phenomena of sp mixing happening in carbon, which essentially what it does is Pz comes a bit down. When we think of Pz, it comes a bit down. When we think of 2s, it comes a bit up. This degeneracy breaks because the s orbital cannot interact with px and py until the point that we consider z to be the internuclear axis. Now, what is going to happen is, when we see this, first I'm going to talk about the simple stuff. When this pi set is going to be formed, this is going to be very simple, as the energies are kind of similar. This is a bit lower than this part in my drawing. this is going to be the pi set that is going to form by the interaction of these two. This is the pi set that is going to be formed by them. Now also there would be a pi star set that is going to be formed corresponding to that. Now what we see is this 2s, as it has come a bit higher in its because of the second order orbital interaction that we saw with 2pz, it is good enough to interact with this 2pz. Now this, what this does is, this comes in, this is what happens. This 2s combines with this 2pz, now forming a sigma sp and a sigma star. Now what remains for us to deal with is this and this that we thought of, the 2pz. Now when we think of it, this thing has come a bit down, but and also this this is also not very well went into some bonding or anti-bonding interaction. This has not really bonded, so we principally call it a non-bonding molecular orbital, the one that we are going to form, because as you see, when a molecule forms, the existence of atomic orbitals becomes a mere fantasy. Atomic orbitals don't exist after that. We talk of molecular orbitals only. So when we think of the molecule, this is going to behave like a non-bonding molecular orbital. But this is not where you stop. I'll come back to this. Now, similar to that, we'll see, because this 2s doesn't have anything to interact with this. This is also going to form, I'll say sigma naught and sigma and b naught. This is just a name that I'm giving. You can just call it an NB. Now, when we start filling in electrons, we'll start from the bottom. We'll see this, and we'll start filling in electrons this way. How many electrons do we have to fill? 1, 2, 3, 4, 5, 6, 7, 8. Now we go from there. How many have we filled? We have filled. Have we filled 8 electrons? Yes, we have. So now, when we see these, see this, it seems simple enough, I suppose. This is not as complicated as you thought of it. But there is one intricacy, the intricacy of bond order. The intricacy of bond order. As I told you guys in the last class, this is something that's based on the difference of energies between these anti-bonding and bonding orbitals, not exactly the Np minus Na by 2 picture that you know, not exactly that. Now, but when we think of our convenience, when a bonding molecular orbital is low enough and an anti-bonding molecular orbital is high enough, we think of this to be our general way to go. But when we get lost in such boundary cases, this thing has not bonded, but this thing has come a bit down. What we do in these cases? Now, when we think of it, these two orbitals as these, if they would have completely mixed. Think of it as if they would have completely mixed. Where would they have ended up? They would have ended up in the middle of these two orbital sets. Now, when you compare it to that middle, this thing has higher energy in comparison to that middle. So now I am going to quote something that is going to sound very counterintuitive, but this is a non-bonding molecular orbital with a slightly anti-bonding character. Now this is where I start beating my head in the wall. What do I call bonding? What do I call non-bonding? And what do I call anti-bonding? So this is where we cannot draw a line. When we see boundary cases, we rely on computational observations. When we see clear enough difference, we call things that are low bonding and the things that are high enough anti-bonding. But when we are dealing with boundary cases like this one, we should always rely on computational data rather than just relying on our intuition that this goes high, this goes down. This is something that comes out of pure computation. Now, this being slightly anti-bonding, you must have heard of bond orders of CO being 3.5 and all that. You must have heard of the bond order of say CO plus maybe 3.5, but actually it's not the case. When you when you think of CO in the classical valence bond picture, you have 3 bonds, right? But now when we start thinking about this, if we remove one electron out of this, if we say generate CO plus from your, if you consider this to be anti-bonding, purely anti-bonding, you will think of the bond order to be 3.5. You think of the bond order to be 3.5, but when you think of computational data, the energy data that we see, it is not 3.5. It is somewhat greater than 3, but it is somewhat greater than 3, but less than 3.5. I'd rather say it is much lesser than 3.5. It is somewhat around 3.2 if you actually see the computational data. That is where things get very interesting. So this was the case of carbon monoxide. If you are not clear with anything, just tell me right now, because this thing I believe is going to trouble a lot of you. If there's anything you can forget.
ऐसे भी मिक्सिंग है, तो वैसे भी रेडी मिक्सिंग होने बाद सबसे ज़्यादा होगा एटली मॉडल सबसे ज़्यादा कैसे सबसे ज़्यादा कैसे पानी को एक्सीडेंट कर गई जो बाइक का सबसे बड़ा है सबसे
क्या चीज़?
होमो
हाँ, ये वाला इतना ज़्यादा क्यों होगा कि पाइप का एक्सीड करने में कुछ now the thing is when we talk about it अपना जब when we think of it as say the gap between these two, when we think of the gap between these two, this because of the overlapping extent as well as we talked about it, the overlapping extent between a S and a P is much more than a pi, because which is why when we even think of anti-bonding characters as well, this thing must compensate, this lowering must compensate somewhat in the hiring of that energy. So if this is lower than this pi set, this sigma is going to be higher than that pi.
प्लस का फोर ऑर्डर तो वो कंप्यूटेशनल डेटा के किसी पर 141 स्लाइडली एटली मॉडल
हाँ, if we
इसका एक्सप्रेशन नहीं है
when we explanation I gave you the explanation. When you think of SP mixing, then you reach this conclusion as well. SP mixing is something that came much before this. When you start say building from that point and compare that intuition to your computational data, then you end up with this. But as the philosophy of chemistry is, you first observe things and then try to explain them, rather than modeling them beforehand. I hope this thing is clear enough to you guys. This is something that confused me a lot. One thing I should also explain, I suppose. If you have heard of synergic bonding, when you were in class 12, maybe they told you guys that when you connect CO to a metal center, we'll be talking about this when we talk about coordination chemistry. This thing also accepts pi electrons. This has some pi back bonding associated with it. How is that possible? This pi star that you are seeing here is what is essentially possible for that back bonding that you talk of there. And also when they make you compare those bond lengths and all, they tell you that as this bond grows stronger, the M and C bond length decreases, but this bond length increases. Why does that bond length increase? Because the electrons are going to the anti-bonding molecular orbital, and when electrons go to the anti-bonding molecular orbital, the bond goes weaker. When the bond goes weaker, it stretches. Now on a similar note, I leave you guys with an exercise to draw the molecular orbital diagram for C and negative. What you need to keep in mind while doing this is that this thing undergoes SP mixing, and this thing undergoes SP mixing as well. This is something that you guys should be able to do now. After you compare both the boron case and the case that I just described right now, you will be able to do this very easily. Now, for me going much deeper into molecular orbital theory, it requires time. But now, as we have a bit of a time constraint and we are not going to have a lecture the next weekend, so I'll be covering over some things that Dr. Devashish has gone through. As I was told, he has gone through HSAB and polarisability. So I'll be talking a bit about that. Now, we are going back to the first thing that we talked about, an ionic bond. When we modeled an ionic bond, we thought of just this, something positive lying around with something negative. But when you start thinking about this, and also start making observations. Let me give you an example. The example of AgCl. When you put AgCl in water, what is it? Is it a precipitate or does it dissolve? AgCl is a precipitate in water. Why is that? This thing has plus, this thing has minus. Water should be able to pull them apart. Why is that? Yeah, this is something where we are trying to build our intuition upon. Now, when you think of this, what happens here is that this positive is when you compare it to Cl, the Ag plus ion is much smaller when you compare it to Cl negative ion. Think of it, and also when you say this, both of these effects come in synergically in order to do this phenomena that I'm just going to describe. This plus charge, because of being dense, because of this charge being over a small sized atom, this is going to essentially pull electron density towards itself. Now, where does it pull electron density from? From this pulls electron density from the nearby nuclei, the negative nuclei that it has, the negative ion floating around it. It pulls away electron density from here. When it pulls away electron density from here, then the electron density basically goes closer to Ag plus. What does this phenomena consequentially do? This causes a deficiency of electrons from where electrons are coming. And now this thing, what this resembles is, if you think about it, two atoms with some electron density between them, this very much resembles our notion of a covalent bond. Now, when a scientist named Fajan made his observations, he talked about this phenomena and called this covalent character in an ionic bond, because the electrons are not centered over the negative ion right now. They are somewhat between the two ions, the sort of ions that we were talking about. This also causes the distortion. The distortion that you talk about is essentially the electron cloud. When electrons clump at one side, the cloud kind of gets the radius of that balloon that you think of increases towards that side. This is where we talk about covalent character. Now, when you try to think of the factors that this thing is affected by, you come up with you need two things to consider. You have a positive ion to consider, you have a negative ion to consider. Now, this positive ion, as small it is, as localized it is, as not spread out it is, it attracts more and more electron density towards it. So, when the size of this is small, and this thing, if it has enough space on it, if this sphere has enough space on it for this negative charge to go towards the positive charge and leaving an electron density behind, creating sort of a dipole, sort of an electric dipole within the ion itself, then its size got to be large. its size better be large for this phenomena to happen. So when we talk of covalent character, we say when the size of the cation is small and the size of the anion is large, these give rise to a molecule with a highly covalent character. Now, when you do all this, in the midst of all this, you just come to the fact that everything is the same. It is similar to when you guys would be told about the fact that electric field and magnetic field are essentially the same things when viewed from different perspectives. This is kind of similar to that. So no bond is purely ionic, no bond is purely covalent. It's all about character. Now, the term that I missed while explaining this was polarizability. Polarizability. The larger the ion is, the more is for it, the better possibility of that dipole being created in it. That is when we call the ion is more polarizable. So that is directly correlated with the size of the anion and something called the polarizing power. This is concerned with the size of the cation, which should be smaller, as we just tried to explain ourselves. Now, when we are talking about sizes and charges, from here I skip through completely, and I'll start going over something called an acid and something called a base. Why do you need terms like acids and bases? Why do you even need terms like acids and bases? You can just think of molecules reacting in between them and just producing something. Why do you need these terms? You need these terms in order to generalize the pattern of reactions, the pattern in which molecules interact with each other, and the kind of molecules they form as a result. Now, when initially people tried building a notion over acids and bases, came in. The first in the list came in the scientist Arrhenius. He said when you dissolve something in water, if it furnishes H plus ions, it is an acid, and something that furnishes OH minus ions is a base. But that generally, this notion requires for a molecule to have an H or say an OH. But when we see reactions around us, we don't just see H and OH, we see other stuff as well. We need to generalize it more. But along these lines also came Bronsted, Lord. He said something that furnishes, similar to Arrhenius, this is called an acid, and something that takes up H plus. This is a base. Something that takes up H plus is a base. Now, this kind of explains something. This gives us a notion of how hydrogen bond works consequentially. I'm not directly going to talk about it right now because we have important stuff to deal with ahead. Now, then came in the general notion of say an acid and a base. Then came in Lewis, the same guy who gave us the structures that we draw for valence bond theory. He came in and he said something that gives away its lone pairs, it's called a base. Something that takes up lone pairs is an acid. Now, when you compare it to Arrhenius's notion and you compare it to Bronsted notion, it is completely consistent with that, and also tries to say generalize other stuff as well, and takes in consideration almost everything, every reaction that we can think of as. All reactions are essentially a transfer of electrons. And when we start thinking of in terms of electrons, everything becomes simpler. Now, not everything has lone pairs, not everything gives away lone pairs, not everything takes away lone pairs. We need to have another notion for this as well. We need to have a middle ground as well. Just like we had when we were talking about orbitals, we need to have a middle ground for acids and bases as well. This is where HSAB comes in. This gives you a notion of reactions more than what it would have just when you were talking about basic definition of acids and bases. Now, what is it called? As you must have been taught by now, hard, soft, acid, base. Okay. Now, when I say hard, when I say soft, these terminologies are very vague in themselves. What is hard and what is soft? Now we fall back to the point where I left off. Point where we left off. Something that this theory is all about charges. If I would frame it like that, this theory is all about thinking of charges and how concentrated they are. This theory is all about charge density. And when we think about charge density, we need to think about two factors of an atom or a molecule. We need to think about the size, as density directly correlates with volume, and we need to consider charge. When is something charged? Either when there is actual charge present, or there is a somewhat partial charge or an electric dipole within the molecule itself. Size is something that we are very much aware of. Now, when we compare it to the notion of polarizability that we built, something that is some ion that is very large in size but has the same magnitude of charge as an ion that is somewhat smaller. The larger ion will have its charge more spread out. The larger ion would have a more polarizability. That is what makes it a soft entity. Now, you'll get more of this when I try to illustrate this with an example. For now, just hear me out. When we think of the contrary, we think of an entity called hard. The more you correlate with the charge density, the simpler it becomes. Now, if you remember a reaction from class 12, I would say, do you remember this reaction? Do you remember this from class 12? How does this reaction work essentially? This reaction works in a sense that this thing is plus, this thing is minus, this thing gives away Now this negative, there is a reason I drew it here. Why not on boron? Boron has more electrons than it should have. Actually, This is where the difference between a formal charge and a real charge resides. Boron is something so electropositive that it cannot actually have a negative charge in its entire lifetime. It would never have a negative charge on it. But when you think of it, this charge is most likely distributed all over the molecule, over all of these hydrogens, because hydrogen it has deficiency of one electron, along with the fact that it can give that one electron that it has. It also can take up electron density on itself. That is why this charge spreads out on the whole molecule rather than being on boron. Although I might say that this is negatively charged, but it is not actually negatively charged. This is just a formal representation. Not exactly hyperconjugation, I would call it a spread of charge. You would think of this whole thing as being
conjugation में bonds ऐसे break होने का मतलब pi bonds जो है वो fluctuate होता है इसमें
you think of this, if you think of this whole BH4 thing as a sphere, this negative charge essentially spreads out on the whole sphere. Now, what this does is, this thing has a delta plus on it, this thing has a delta minus on it. This hydrogen is going to go here, these electrons go here. This gives you along with the BH3 that is going to dimerize because of its say electron deficiency, the banana bonding that you study all the time. Now this is the ETOH. It is now going to come in handy. This negative thing comes in, this takes it away out. Now you have what you wanted. This reaction is simple enough for us to understand, but a similar thing happens when I treat the same thing with this. A similar thing happens here by the same mechanism that we thought of here. But now, what if I take another molecule? What if I think of this thing? What if I put another double bond here? What does this do? This double bond, because of this oxygen trying to pull away all the electron density that this molecule has, it pulls this away. This goes here. Then we have a resonating structure for this molecule. We see this going away, so this is going to have a plus charge. This going here, this having a negative charge. And we see somewhat, this thing was delta plus here, but there is a whole plus charge here as well. So in the whole molecule's resonance hybrid, you would have a delta plus here, you would have a delta minus here, you would have a delta plus here. Now, there are two sites where the H can go. The H that was being removed, that can go. Now, when we think of this reaction, and we see weird results when we react this molecule with, say, when you react this with NaBH4 and you react this with LiAlH4, you would see weird differences that you would not be able to explain with plain theory. Then we require HSAB. Then we require the notion that we just built, the notion of charge density. Now, when we are thinking of this molecule, when I think of it interacting with I think of this interacting with ALH, and also when I think of it interacting with compare, because the bonds that are in play, the bonds that are going to break, the Al H bond and the B H bond, these are the bonds that are in play here. Now when we think of it, B and H are somewhat say closer in terms of their position in the periodic table. So this bond is not very much polar. I have not said that it is not polar, but it is not very much polar, not at least not as polar as ALH would be. Also, when you think of it, when I compare sizes, when I think of comparing sizes, if I would give you a scale, if this is H, this might be B, but AL is this. When you think of comparing sizes, you end up here. So now, when you think of compatibility or overlapping of orbitals while this reaction is happening, when we think of compatibility, this brings in also the charge suiting the site and also the size choosing the site. So this thing being say more polar, this thing being more charged, more dense in terms of charge, this would prefer to go at a place that is more dense in charge in itself. That is, when it would try to be as compatible with the site as much as possible. So, which site out of these two do you think has a more localized charge? Which site out of these? Because both of these sites are charged. Which site out of these do you think is more charged? Yeah, just because of the fact that this thing is going to stay here. The C double bond O dipole, the individual C double bond O dipole, this is going to be very strong. This thing gets charged up only in one of the resonance contributors. This is not in both of them. But in this case, this dipole is much stronger. This charge is much more dense, and which is why a dense charge prefers a dense charge, which is what we call hard prefers hard. Now what hard, what soft? We think what we try to generalize. We try to generalize all reactions under the umbrella of acids and bases. So something that gives electrons is a hard base. Something that takes up electrons is hard acid. So hard acid prefers hard base, or the vice versa. Now, what we are going to see is when we do this reaction with LiAlH4, what we are going to see is this thing goes here, because this bond is much more polar. This charge is much more say dense in here, and this goes in here. These pi electrons go away, and the product that we are going to get this pi bond stays here, stays preserved. This gets an H. This is going to become when it takes up an electron from the say, when we do a workup, when we give this some water, this is going to form this, right? But on the other hand, when we think of the hydrogen that we are going to get from here, this hydrogen goes here. When it goes here, this bond got a break. This is essentially reacting with the other resonance contributor that we talked of earlier. This is reacting with that contributor. So this thing goes here, this thing goes here. This hydrogen is over here, that came in. Now this, when it say gets H plus from the medium, this is going to form an enol. Enols are not stable in their true sense, so they are going to this is going to convert into its keto form. So I'm skipping that part as it's not very relevant. This is going to form this. Now, as you still have some NaBH4 left in your solution, So this is going to further react, and going to react in the similar fashion as it did when we talked of the earlier reaction. This is going to form this. So this thing has no double bond here, but this thing has a double bond here. So this dichotomy arises due to hard preferring hard and soft preferring soft. This essentially is an example of soft acid preferring a soft base. That is where I'll give you guys a break. I'll get a water break myself. Okay, so as everybody is aware now, so something that a few of you asked me in the initial few lectures is about the radial wave function plot of the 1s orbital basically. So now, what you guys asked me essentially was, when I draw this, you have something of this sort. If I try to draw it exactly, yeah, you get something of this sort when you think of 1s orbital, when you solve the Schrodinger equation for it, you get something of this sort. And also, you get something of this sort as well. Now, what is this and what is this? Now, if you remember, you were told about two things. You were told about this, and you were told about. Now, what is the difference between these two? Now, here comes the difference between a radial wave function and a radial distribution function. For now, what do you understand by both of these terminologies? I would like an answer. What do you understand by both of these terminologies? From what you know from earlier or maybe Dr.
रेडियल डिस्ट्रीब्यूशन फंक्शन तो उसका ये होता है प्रोबेबिलिटी डिस्ट्रीब्यूशन है.
हाँ, रेडियल वेव फंक्शन क्या होता है?
वेव में आई थिंक
Let me put it this way. Radial wave function
फेज को डिफाइन कर
is exactly what you have for the wave, just like you had it for your wave, say sin omega t. This is a wave function. When you convert this, when you mold this in your for your convenience into representing an electron using the Schrodinger equation, that becomes a radial wave function. That is just the position, essentially the position of say the constituents of the wave. Nothing apart from that. Now, when you might notice, I didn't mention any y-axis in this plot. I didn't mention any y-axis. When I'm talking about this graph, I will have the y-axis to be psi. But when I'm talking about this graph, I'll have the y-axis to be this. I would say this is what would be the y-axis here in the case of this plot that you are getting. This is the radial distribution. But this is the radial wave function. Now I might conclude by saying that as this is the radial distribution, this represents the probability which is 0 at the nuclei, and just brush off the possibility of why this starts from a maxima. But I'll elaborate on the fact that why even this thing starts from a maximum rather than being 0. When you think about say, have you heard of this expression? I suppose you have. the spin angular momentum of an electron in lying in an orbital with a azimuthal quantum number of L. Now, I would want you guys to assume this for the time being, because even I am not educated enough to teach you the derivation of this. So, when we think in this manner, if something, what does it mean for something to have an angular momentum? There is something that is spinning or something that is rotating. When we think of it in the sense of something around a sphere, you would think of something spinning, or there is a circular component to it. Now, when you start thinking about, say, s orbital, for this the L is 0. For this the L is 0. So essentially what this means is there is no angular momentum for it. The angular momentum is 0. There is no, when we say that the angular momentum is 0, one thing that we are also implying from that is that the centrifugal barrier, or basically the centrifugal agent that there would have been if there was a non-zero angular momentum is absent in this case. There is nothing pulling that electron away. So that is why the wave function tries to be maximum at this point. While if you think of any other L which is not equal to 0, this thing won't be a maximum at r equals 0. The absence of this centrifugal agent essentially eliminates that pull that there would have been if the angular momentum component was non-zero. Yeah. So as you guys have a class after this as well, I end it here. If you guys have any doubts from what Dr. Devashish has said, you might ask me for the odd 15 minutes that you have. Yeah. Also, you can compare the radial function and radial distribution function of other orbitals as well, as you might see in your textbook. You will notice that for any other orbital when compared other than S, you will see that the wave function would never start from that maximum value. It would start from rather, I would say, something less or maybe 0.
Yes.
Yeah. That this centrifugal agent is the reason for that.
ये में सबसे मानते हैं गराडेड अनगराडेड का गराडेड इसमें सेंटर से बैटरी होती है अनगराडेड से सेंटर से बैटरी नहीं होती है
Graded means if you go from the center of an orbital and if you go in radially any direction, you draw a circle around the orbital, keeping its center as the center of that circle. You go in any direction. If you can exactly radially, or if you can find electrons in the radially opposite direction as well, or with the same phase, then the orbital is Garade. Otherwise, the orbital is ungarade.
मतलब अगर एक पॉइंट सेंटर से मैं इधर चलूँ तो मेरे को भी सेम फंक्शन का इलेक्ट्रॉन मिलेगा पॉइंट 0 से मैं इधर चला अपोजिट डायरेक्शनली तो भी मेरे को सेम फंक्शन का
तुम्हें जब तुम यहाँ से चले तो तुम्हें इस डायरेक्शन में सेम मिला, इस डायरेक्शन में सेम मिला, ठीक है कि कहीं इलेक्ट्रॉन तो इधर सेम मिला, इधर सेम मिला, इधर सेम मिला, इधर सेम मिला। बट जब तुम यहाँ से जाने लगे दोनों जगह फेज ऑपोजिट मिला, तब ये अनकराटे है। जब तुम्हें दोनों जैसे एस है, तुम्हें इसमें तुम इधर जाओगे तुम्हें तो भी कराटे तो भी ये मिलेगा, इधर जाओगे तो भी ये मिलेगा, तुम इधर जाओगे तो भी ये मिलेगा, इधर जाओगे तो भी ये मिलेगा। ये तुम्हारा कराटे है। बस तुम्हें ऑर्बिटल के अराउंड एक सर्कल ड्रॉ करना है एंड उसकी जितनी पॉसिबल रेडियाई है उन सब में ऑपोजिट जो रेडियाई होगी वहाँ पे सेम होना चाहिए बिहेवियर फंक्शन का।